Right, good evening everyone. Astronomy 10, Intersection, Evergreen Valley College, and I am Celso Battaglia. Okay, so this week, that's the second week, from 8 to 13, we are covering basically how stars in general are formed. And yesterday we focused on the sun, how the sun is formed, and then we highlight the main ingredients in the formation of a star. You gotta have gas and dust, and gravity has to be efficient in certain regions of a giant molecular cloud so that gravitational pull will bring gas in. But since these giant molecular clouds interact among themselves, then here and there in the cloud you have rotations or vortex in different directions. So when gravity starts to clump gas here and there in the molecular cloud, the rotation becomes um, significant. The angular velocity of the rotating gas becomes significant. It's sort of the ballerina effect. So the ballerina or ballerino, they open their arms and they initiate a rotation with small velocity or angular velocity. And as they bring the arm in, and then think about gas collapse into the center of mass of that system. So as more material get to be brought towards the center of mass, that system rotates faster and faster and faster, and then it spins up. Um, and as the gas is spin up, now if you are going to be a graduate student in astronomy, you're going to learn how this flattened disk forms as a result of the laws of conservation of angular momentum, conservation of energy, and gravitational forces, basically. And then this flattened disk forms around the star, better saying, around the protostar. And then as the protostar contracts more and more and more, think about a gas that gets to be collapsed and contract strongly. Then the particles in this gas will be forced to collide among themselves because there will be less space for them. The volume is diminishing. And as the volume diminishes, there is less space for them. They react with this confinement with mobility. They become more mobile, faster. And in physics, we would say their kinetic energy increases. And, and kinetic energy, as we learn in physics, is associated with temperature. So when the gas moves faster, the temperature grows up. Okay? So as the central star collapses and contracts, it heats up. Now we have this hot star in the center, we have the circumstellar disk around, the heat radiates away from the star so that it will control the type of grains that are formed in the circumstellar disk. So close to the star, you can only form metals and metal oxides and silicates, solid dust, rocky material. But in the regions further out, you can form that plus ices, all kind of ices. And that's why our solar system, when it's formed, is segregated in two main regions in its disk. The region in the disk closer to the star has more of the metal or rocky type of material, and the regions further out has more of the volatiles and the icy types of material. So closer to the sun, you might find leftovers, junk material, we call asteroids, in the regions further out, in the Oort cloud and in the Kuiper belt, we have the leftovers and we call them comets. So the difference between comets and asteroids is in their composition. So asteroids are closer to the star, rocky type. Comets are further out, they are formed further out, they are pretty much icy type. But they also have dust and grains, and it's always fun to collect their material because we can learn about the origins of our solar system. So we kind of saw this yesterday, and um, today I would like to focus on our sun and properties of the sun and its interior part. And then tomorrow on Thursday, I would like to talk about properties of stars and star formation and evolution. And then we close the subject of this week. And the subject is what's going to be tested in midterm number 2. That is going to be open on Monday and reopen on Wednesday. By the way, today is Wednesday, and there is a midterm number 1 still open. Have you done twice? Have you done the 2 attempts? You should try. I will pick up the high score, nothing to lose, only to gain. Okay, but I said yesterday I would like to show you some simulations on prograde and retrograde motion, and I kind of put them together. Oh, that's not it. It's good news. Oh my lord. So hard to open the newspaper, but here they are. Okay. And there are 2 worldviews we are studying, and they are directly related to the subject of prograde and retrograde motion in our solar system. Several of you, I have tried to bring you guys to verbalize, and I think this question was in the exam, to verbalize that when we talk about prograde and retrograde motion of planets, prograde and retrograde motion of planets is with respect to the stars that happen to be in the sky, right? Of course, there is no sky stars in our floor. Probably your daughter, your son are stars. But you know what I mean. Stars in the sky, in the celestial sphere, which, by the way, does not exist. Not in respect to the horizon. Horizon is this imaginary line that divides the sky and earth. Very far away, if you take a plane, cardboard passing through your eyes and parallel to the floor and extend it out to the infinite. That is your horizon, right? So the diurnal motion, the east to west motion of stars and planets, and let me show you here in Starry Night software. There you go. So this is diurnal motion, the east to west motion of stars as we face south, caused by Earth rotation in the sky. So as you open this, as you look at this time flow, and it's flowing very fast. So look at this, 3 in the morning, no, 3 in the afternoon, 4, 5, it's going very fast. So as time speed up so that we can see this diurnal motion more efficiently, we should realize that in fact, Earth, the ground, where you have these fake trees and the fake mountains, the ground is the one that is spinning, it's spinning from the western part of the sky, so your right-hand side as you look at the screen, to your left-hand side, the eastern sky. So that is what Earth does. And by doing that, we have this illusion that stars are the one going around us. And the geocentric worldview bought that idea. The geocentric worldview considered that the stars, the sun, and the planets were the one going around Earth, and Earth was the center of the universe. The Catholic Church bought this idea in the Middle Ages, and in Renaissance was strongly defended by the Catholic Church, especially because certain parts of the Bible would indicate that Earth had some importance among everything else in the universe, because was the place where God had set the base for man and humanity to develop. But anyways, that is geocentric worldview. How do we explain prograde and retrograde motion in geocentric worldview. That's where the animation goes. But before I show the animation with the interpretation given by geocentric and heliocentric worldview, let me show you from the perspective of somebody here on Earth what those motions represent. So I will stop this now. I did. So I stopped the motion. And what I'm going to do, I'm going to be facing a sky region. I'm going to be facing a sky region always. Who likes Leo? Look at Leo over there. So I'm going to be facing Leo, Cancer, Gemini. I'm going to be facing this region here forever. Okay. And I'm also going to bring the labels of planets and moons. So the moon is there. Uranus is here. It's very faint, so we can't see it. Pluto, poor Pluto, is not a planet anymore. It's a dwarf planet. But Saturn is right there. Jupiter is there. See that? Jupiter is right there. And Saturn. And what I would do is to, as I fix this region in the sky, imagine that, in fact, I'm not going to imagine. I'm going to do some exercise. We are going to take a trip to the North Pole. I'll do it right now. North Pole. There you go. I'm going to go faster. Okay, we are there. North Pole, right? Not only that, I will take a spaceship and blast off. Yeah, there you go. See the atmosphere? We are going above the atmosphere, and Earth is down below. And here's the region we were looking previously. Oh no, it's not the region. Where is Leo? There you go. Leo, Cancer, and Gemini. Leo, Cancer, and Gemini. So see what we did? We went to the North Pole, right there in North Pole, and then we blast off. We move with a rocket, in fact, 5,000 kilometers above Earth's surface. And then we can look down, and Earth is right there. Look at that. See the Earth right there? North Pole is right there with that red line. Santa Claus is making a lot of toys for the kids. And now we stare at Leo, Cancer, and Gemini region, and we'll forget about Earth spinning. But we will not forget about Earth's revolution around the sun. Remember, there are two types of motions that we learn in chapter 2. One is Earth rotating on its axis, and the other one is Earth revolving around the sun. Revolution and spin or rotations are two different things. They both involve rotation, but rotation itself or spin is when the body rotates around a line that passes through its body. Whereas revolution is when the rotation is done as the body revolves around a line that does not pass through its body. So the line Earth revolves to is the line that passes through the sun. Does that make sense? It's not on Earth. So we are, again, ignoring Earth rotation. So if you could look down below, you would see Earth rotating, right? Spinning. But we wouldn't be rotating with Earth. We would be stationary, facing the same sky region all the time. But we are co-moving with Earth as Earth goes around the sun. We are revolving around the sun as Earth does. And we are taking 365 days and a quarter to complete that revolution as Earth does. Okay, so if we do that, one day later, the moon moves to the eastern part of the sky with respect to what? Not our horizon, because our horizon is spinning up. It has nothing to do with the horizon. But with respect to the stars we are observing, with respect to Leo, Cancer, Gemini, and then another day goes by, and the moon is changing its phase, is going waning crescent, right? It's going towards the new phase. And another day goes by, and another days go by. We don't see a lot of emotion in Saturn and Jupiter. They seem to be very slow. Now imagine that you are somebody living 2,000 years ago and take note of all these observations. You go the next day and then you mark with rocks and send the position of the stars in the sky. You make configuration and then you notice the moon goes across the stars from your right hand side to your left hand side. And somehow you learn to define north, south, east, west, probably using sticks and shadows. Now imagine you could do that for the entire year. And every day you go there and you have a special place with the rocks. No one goes there to mess with you. And then you allow this to happen very fast. And then you take notes of that. And that's what I'm doing now. So you notice that certain object, moon is always going from east to west. But look at this. Mercury, the planet, retrogrades and then progrades. Look at Venus. Venus is, see the comet? Venus is prograding all the time here. But Uranus in the right hand side, right in the corner, is retrograding and now is prograding. Look at that. He's moving with respect to the stars from the western part of the sky to the eastern. And the sun is always going from west to east. So sun always progrades. The moon always progrades. Saturn in Leo is retrograding. All Jupiter in Cancer, not in Cancer, in Virgo is retrograding now, progrades, and another year went by and the sun is passing by. Saturn in which constellation? Virgo is pretty much was retrograde and now is prograding. Keep a look at Saturn. Saturn still progrades and we'll start retrograding now. Look at that. And Saturn now retrogrades. And there you go. So in the ancient astrological system, these planets were not planets as we know today. We know these planets having silicon, oxygen, and hydrogen, helium, and so on, so on, so on. But in those days, these planets were thought to be gods. They were thought to be some super Marvel heroes, and they had some properties of, and we were born out of them. I mean, some cultures, we share aspects of these gods, and we have these two properties of being mortal and the property of being immortal. And that's why we are always in conflict. It's beautiful to read their interpretation of that. And why they associate the stars and the planets with godlike figures. Because the stars are and the planets always repeat their motion. It's very regular and it's very harmonic. And that's why they try to fit these objects, since they thought they were gods, and the most perfect representation of God in all cultures is a circle, right? Is a circle. So their motion should be circular. And Ptolemy came and inherited this idea and create the geocentric worldview to explain progression and retrograde motion. So if this Earth were in the center of the solar system and planets would go around in circles, we wouldn't observe retrograde motion. But the genius Ptolemy did the following. Let me show you this. And here is what he did. So he put the Earth in the center first, but the center didn't work fine, and then he started kind of moving Earth around in a complicated way, just to make sure, um, the data in his model would meet with accuracy the observations. So this first circle here is called deferent. So deferent is a circle in which the center of the planetary orbit is located. See this red ball here, this red circle? This red circle attempts to represent Mars. I could try to represent Jupiter, for instance. Right? But let's do Mars. Can I do Venus? Yes, I can. Let's do Venus. Venus is good. Let's do Venus. So here's Earth. Venus is there, but Venus doesn't go around Earth. Venus goes around a circle that has a center in another circle called deferent. Now, as Venus goes around this deferent, sometimes it goes forward, right? But sometimes has to go backward. And then we call that retrogradation. But you see, when Venus retrograde, Venus is also closer to Earth. And that's why the observations these ancient astronomers did was exactly that. When Venus was retrograding, was brighter. And now these astrologers in those days, since they thought Venus was a goddess, they put a lot of meaning in the fact the goddess now was retrograding, was not in the normal phase of her life, and was brighter than in any other phase. And that has some interpretations. They create that interpretation in psychological ways, so on, so on, so on. But let's see how that goes. See that? And let me stop. Right here. So see this little tiny moment right here? I don't know if you can see my cursor, but if you can, this little tiny moment that Venus retrograde, it also happened to be the position in the orbit part that Venus is the closest to Earth. And then it matched quite well observations. Mars was, since Mars orbit is not exactly, is very elongated, Mars was giving up some problems for this type of model and was not fitting with results, with good results. Now look at the sun. The sun is always going in the same direction. The sun never retrogrades. The sun is this yellow circle, right? This is the geocentric model. Earth in the center, the planets going around a deferent. The deferent orbit Earth, and everything goes that way. Now, in the case of Venus, pay attention to something interesting here. Venus and the Sun, if you take a line from Earth to the Sun, Venus happen to be always close to that line. Keep observing that. See that? Venus is never in the opposite side of the Sun. It's always in a line connecting Earth of the Sun and the Sun, and this is pretty much observable. Venus is the morning star or the evening star. When the sun is rising, Venus is there, or when the sun is setting, Venus is there. Same thing with the Mercury. Let me show Mercury here. Oh, I don't have Mercury. That's too bad. Now, if I bring Jupiter, for instance, Jupiter sometimes is closer to the sun in the line, but sometimes in the opposite direction, like now. See? So Earth is here, Jupiter is there, and the sun is not in the line close to Jupiter. And so what Ptolemy did, he established a line from Earth to the sun, and then he forced Mercury and Venus to be always in certain degrees close to that line to match observations. So it was a complicated model, but it works, right? It doesn't fit reality because Earth is not the center of the solar system, but it matches observations. And that goes to the point that I would like to highlight to all of you, that in science nowadays, you can say anything that fits the data, but what you say that fits the data does not constitute science. To constitute science, you have to test your model. So this geocentric worldview was tested. So you can create tests to verify this model and to see if it withstands reality. So one of the tests that can be done, let me show you here in Venus. Let me go with a small rate in the animation. There you go. That's Venus, right? Venus always close to the sun. Pause animation. Look closely. In this animation, Venus is always in between Earth and the sun. Is that correct? Venus is never seen beyond the sun. Is that correct? It's never there. Now, I don't know if you can follow me here, and I try to be as clear as I can. Venus is a planet. It doesn't have proper light. Sun is a planet, is a star. It has proper light. Sun is the luminary of our solar system. And if you look at Venus' position in this model, Venus, as observed from Earth, should always be in the crescent phase. Right? Gibbous phase, as we learn in the Moon, for instance, is a phase in the planetary configuration in which the planet is seen in opposition in respect to the Sun. So you have Earth, and then you have the Sun, and then you have the planet, right? Beyond the Sun. If Earth was in the center of the solar system, for Venus to be in gibbous phase, Venus should be further away from Earth than the Sun is. Guess what? Galileo Galilei observed that, and we saw that in chapter 3. Galileo Galilei, with a telescope, was able to see Venus in gibbous phase, which means Venus was in a position that was beyond the Sun. Okay, let's go to another one. That's the heliocentric worldview. Right? The heliocentric worldview, you have the Sun in the center and the planets go around the Sun. Now, look at this animation and you see the planets closer to the Sun, they are faster. Whereas Saturn, Jupiter, for instance, they go very slow. See that? It's Jupiter right here and Saturn right there. The speed is less. And we learn this as one of the outcomes of Kepler's law of motion that was brought into theory by Newton's law of gravitation in the 1700s. And with those laws, we can explain that planets closer to the Sun, they go faster than planets further out. So let's now look at this planet configuration as seen from Earth. Here's Earth. Earth is not in the center of the solar system anymore, but is just another planet. That's the Sun, and this is a ulterior planet. That could be Mars. If I start animation, planets go faster, Earth goes faster around the Sun, then Mars goes. Now, look at this drawing, this animation right here. The sun is always prograding, going from west to east in respect to the stars of the zodiac. But look at the planet. Planets sometimes progrades, like now, and now it's going to retrograde when Earth is taking over, is passing that planet. And again, planet is retrograding and now progrades again. So can explain, or in this simulation, why the planet becomes brighter in retrogradation? Oh yes, look at right here. This is when Mars retrogrades, but that's when Mars is closer to Earth. See that? And therefore is brighter because it's closer to Earth. Now, can we explain why this interior planet, Venus and Mars, or Venus and Mercury, are always next to the Sun? Well, because it's closer to the Sun. We always gonna see them in the sky closer to the Sun. Just imagine there is two balls in between, the yellow ball and the blue ball. But why do we see in this model here, sometimes we might have Earth and Venus in opposition. And in this configuration, Venus will show the gibbous phase. And that was observed by Galileo Galilei. So a simple observation can rule out the geocentric cosmological view of Ptolemy. And that was done by Galileo Galilei with instrumentation. And that is the beauty of science. Once you find the data that challenge a theory, the theory is gone. It has to be put away. There is no remedy. There is no band-aids. You can establish certain band-aids to improve certain theory, but if there are too many band-aids here and there, too many fix-up, scientists don't like that. It's because the theory is not good, and then they have to come up and find something better and more overwhelmingly overarching. Well, I think I took too long in this discussion, but it has to do with this one-on-one discussion that is going to be closed today. So I extended it to Tuesdays. No, I closed yesterday, right? Oh no, I extended to Wednesday. So you can. Did I? No, I think it closed yesterday. Today is Wednesday. What I'm talking about? Sorry. Yeah, I have to correct the progression and retrograde motion. But anyway, I think there are some questions in exam that are pretty much based on this content, and I would like you to know that well. Okay. Do you have any question? And am I missing anything here? No. Okay. So let's take a look at the sun. And for that, let me get origins of solar system. We did yesterday, right? The asteroids and this and that. So I'm not gonna go there. Oh, that's interesting. See, asteroids can hit cars, can hit your house, because it's a small probability, but it might happen. So if it does, the car insurance won't pay. If there is a meteorite hitting your roof, chances are the insurance company the homeowners will not pay for not in the insurance. But you can sell the story and make a lot of money. As long as everybody's safe, that's a good thing. Anyway, so let's quickly look at the sun and go to main aspects of the sun. So the sun is a star, is about 100 times as big as Earth. Uh, Cecilia Payne, she did a PhD. I mean, there is a major contribution of women to astronomy, and only right now these contributions have been um, highlighted and and honored, and these women are being pretty much vindicated by historians and by the work they really did. We are going to study stellar classification, the spectral classification of stars, and this job was primarily done by a battalion of women working uh, to Pickering, which was an astronomer in charge of the Palomar Observatory, and he had a bunch of postdoctoral fellows working for him in this spectral classification of stars. But they were not doing a good job, and these women they really were hired. They were not paid as much money as the men were, but they did an excellent job. And as you study stellar classification in the next chapter, and I will talk about it tomorrow, um, remember their contribution. Now, briefly speaking, how do we divide the sun in three main regions? The center part, the core. The core of the sun is where energy of the sun is produced. And the energy of the sun comes out of fusion reaction. Fusion reaction. So basically, four atoms of hydrogen are fused together at very high temperature to give one atom of the element helium plus energy, and this energy is in gamma rays, and we studied that in electromagnetic radiation. Gamma rays, the most energetic frequency of electromagnetic radiation. So gamma rays plus an elusive particle named neutrino that escapes the sun. Neutrinos interact very little with matter. We have trillions of neutrinos crossing every square inch of our body every second. There is a flood of neutrinos passing by, but they interact very poorly with matter. And so they are not trapped by the sun's interior material. So fusion reactions is the result of what? If you take four atoms of hydrogen, which primarily four protons, and you merge them together, because you exert enormous pressure in the core of the sun at high temperature, 20 million kelvins, then they will fuse together in a process. The main process occurring in the sun has a name called p chain. P stands for proton, so proton chain, and as a result, one atom of helium is formed, plus energy, plus light is formed, and neutrinos that escape. So that is the main contribution of the solar core, the solar central part. That's where energy is produced. Now, there is a second region in the solar interior that is the radiative shell, is the one that I'm outlining here. In the radiative shell, that energy, which is gamma rays, the energy that is produced in the core, floats and diffuses outward. And some of that energy is transferred to the gas and keep it hot. And again, when gas is hot, gas has tendency to expand. And why this is good? Well, because the sun has lots of matter, and this matter has gravity. The gravity is forcing, is bringing the gas to a center. If you don't have some equalizing force in the solar interior or in any star interior, the star will collapse into a black hole because there will be no force that can stop contraction, gravity. So this energy produced in the core diffuses and heats up the atoms, the plasma, in the radiative diffusive shell, and that shell gets hot. And there is a perfect balance between gravity and this outward force that is exerted on the shells, tending or giving a tendency of the star to expand. So the sun doesn't contract, the sun doesn't expand. The sun has kept the same size for millions of years as far as we can testify by its luminosity. The luminosity of the sun can be measured in rocks here on Earth. And then we know how the sun luminosity has been changed over eons. So the last region in the solar interior is here represented by these bubbles, these cells, is the so-called convective zone. Convective zone from convection. See if it's written somewhere here. Convection, convection, C-T, convection. Convection zone, this is an I have, yeah, convection zone. Convection zone. In the convection zone, you have heat that is moved from the solar interior all the way to the atmosphere by mass motion. So gas bubbles up like when you do a soup, right? So when you do a soup, you warm up the pot and then you have this water or the soup content just moving up and then settle down and then goes down and circulates. Earth has convection too in the mantle. So those are the three regions of the solar, oh here, convection zone. The sun has these three interior regions and also has three exterior regions we call atmosphere. And these three exterior regions are the photosphere, which is the most interior part of the atmosphere, the chromosphere, and the corona. So those are the three main contents of the solar interior part and exterior part, the atmosphere. Now the sun, in its atmosphere, in its photosphere, it shows certain features. So these features in particular here are called sunspots. And if you had a chance to go to the observatory this Friday, if you get there early, and if the sun is still in this space, is visible above horizon, we might be able to try to spy some spots. We have an observatory this Friday, and I will announce. I might come up with some extra credit for Friday. But the size of Earth is brought here to compare with the size of these spots. These spots are huge. They are 2-3 times as big as Earth. And the spots are dark because the region in there is cooler than the rest of the atmosphere. And by contrast, we see them as dark spots. The photosphere also has granulation, and you can see nicely in this picture here, this granulation, these cells, they represent convection, the less elements, the less layers of convections in the sun, this bubbling up of hot gas. Imagine this to be living cells of gas rising up and falling down as they heat up the upper atmosphere. And in this group of granulations, you can see a sunspot on view. The sunspot has two main regions, the umbra, which is the dark part. The temperature there is about 4,000 degrees, 4,000 kelvins, and the penumbral part, which is here seen with a bunch of filaments, and they are in general 5,000 Kelvin. And the granulation itself, if you take the average of that temperature, you're talking about 6,000 Kelvin. And the atmosphere, photosphere, is where those features were exist. The chromosphere is about the photosphere, and the corona is the outmost layer of the solar atmosphere. Here's a scale that shows how the temperature varies in the atmosphere. In the photosphere, the temperature diminishes always when it hits the minimum temperature, and then it starts to rise up to the chromosphere and eventually reach corona. Transition region is a very small region, and in some books it's not considered a region exactly. Um, but some authors, they, like in our book, they mention that region. So, and the sun has several activities, and all these activities are related to the sun's magnetism. The sunspots we saw, not the granulation, but the sunspot we saw, the prominences that appear in the very beginning of the chapter. Let me see if I can show here. All this coronal mass ejection, you see here the streaming of gas coming out. These regions called spicules, all of them are controlled by the sun's magnetic activity. See this beautiful prominence here, this arch, are the result of magnetism in the sun that confines the gas in it. Okay. So the sun's magnet is the result of, if you learn in physics, we learn that magnetic field lines can be generated as particles move and rotate. So, for instance, little atoms, they have electrons orbiting the nucleus. And as electron um, orbits the nucleus, you can think of a magnetism being generated by the atom itself. Now, think about the sun rotating and taking 25 days to complete one rotation in the equator. As this gas rotates, this gas is pretty much ionized, it generates a global magnetic field in the sun. And what is being shown in this picture is that these magnetic field lines, as the sun advances in its rotation, these magnetic field lines tangle up and generates all these activities we detect. And stars in general are magnetically active. The extra credit that I posted, and then it's going to be closed, I think Friday or so, on the atmosphere of an exoplanet. The exoplanet is encircling a M star. So M star is magnetic active by itself because it has lots of convection and has rotation. And and then astronomers thought that this planet, exoplanets around M dwarf, would not have atmosphere because of the activity, the magnetic activity of the star itself. But you know, an exoplanet was found with an atmosphere, and I thought that was interesting to be shown. But anyway, more results of the sun's magnetic activity, more in there. Now, the magnetic activity of the sun has a cycle, 22 years, divided in two half cycles, each one of 11 years, in which the magnetic polarity of the sun changes from north to south and reverse 11 years later. So this reversal can be explained by, in fact, the only model that exists to explain the sun's magnetism, and that is called the solar dynamo. That's the name of the model that exists so far, and is the only successful to explain the sun's magnetism, although it's not complete. It has some flaws, but it's the only one we have so far. Um, Now, the sun's magnetism can be mapped by the number of spots, the number of sunspots detected in its atmosphere. And then what is interesting, this number of spots fall down and grow in a time scale of 11 years. So if you go from peak to peak in each one of the cycle here, and these dots, each dot represents these numbers here, 100, 200, 300, 400, represents the number of spots that have been measured on solar surface in a year. And then you can see this maximum number of spots repeat themselves in 11 years. But what astronomers observed was the following. When the new cycle starts and the spots start to appear heavily, they appear at a high latitude. And then as the number of spots diminish, new spots are formed more close to the equator. And then they note that after 11 years, the sun's polarity, magnetic polarity, reverse. And the technique used for that is called Zeeman effect. We learned that in physics. You guys don't need to go in too much detail on it, but what you need to know is that this reversal in magnetic polarity in the sun can be measured using spectroscopy and the Zeeman effect. Okay. Well, that was the introduction to the sun, our star. And we talk a little bit about its magnetic activity. And so again, go to Sarah, especially Sarah, you are reading now, good, very good. I recommend you guys to go to wait a minute. I thought I had brought. I thought, yeah, I did. So, for instance, we take the chapter on the sun, right? And then it's chapter 15. Then you go to the entire PDF, right? So go to OpenStax, right here. No, I don't know. Subjects, science. Find your book. It's right there. And then you download a PDF version. Choose the low resolution because it's faster. And then you're gonna have this thing here. So go to the chapter and key terms. So those are key terms that I will ask question, right? So it's good to know what they are. And you have a nice summary here. See that? And again, I would try to bring questions, more questions, based on these summaries. And also you have, if you want to test yourself, there are some questions here. For instance, why do sunspots look dark? Right? Why are they dark? So they are dark because they are cooler. And they are cooler because that region has lots of magnetism that prevents the hot gas to move up and warm up the atmosphere. I mean, all of the answers are in the book, and it's a nice way to study it if you don't have time. Certainly, if you have a second buddy in the class that could study together, even better. But if that's not the case, you guys can always ask me to answer any of the questions, and I would go there with you. Okay. Right, folks, any question? All right. So then, good night to all of you, and I will start working on the video and upload later in Canvas. Good night to all.